Alright, welcome back here to this video for chapter number 4 of Econometrics EBE2174. For this particular video, the focus will be on the CLRN assumption and the blue properties. So CLRM is actually called Classical Linear Regression Model Assumption and the blue properties. So that's the focus for this particular chapter. Before I forget, good morning, good afternoon, good evening, and good night to all of you, and whatever time you're watching this video. You have a good day ahead, right? So this basically, the chapter basically will talks about the CLRM assumption. This is the focus here, and the blue properties, right? Let us move on. So the learning objective of this chapter is that by the end, you gain some value added, or to know the classical linear regression model assumption, and know the properties under the classical assumption and related, which is closely related to the blue properties. All right. So let us move on. So what is the classical assumption? This is not the classical music also, but this is a classical assumption that as you've been gone through in the previous chapter, the chapters on when you talk about the regression function, the OLS actually divided into the classical and the Bayesian. So this is the part where we talk about the classical school of thoughts or the classical understanding, which is used as the regression model, which we're going to use also for this particular class and model that you're going to use adopted in your project, right? So a classical assumption assume that it's a set of Gaussian standard classical assumption to follow in order for the OLS estimates to display a desirable properties, right? So the interpretation of the regression estimate will be invalid if this assumption will violated or will be violated. So this is what we call is important to fulfill the assumption requirement, or what we call in short as CLRM here. All right, so why a need to have this assumption, right? So the idea is that as the objective is not just to obtain the estimates of the betas, the intercept and the beta, the alpha and the beta, but also draw inferences about the true beta, or rather how close is the estimated beta from the counterparts of the population. This is the idea here. How close of the estimated from the true population means that the sample regression function from the population regression function, how close are we? So that's also the assumption, not only just to get off the estimates, but so the sample plays an important role in this case, right? To represent the population. All right, so that's why we need to make a certain assumption to fulfill the certain assumption in that sense. If this is the population regression assumption, so we need to make specific in the way and to prove it statistically about what the regression is about, the population regression function from the sample that represented the population. All right, if we look back at the history, has been developed in 1821. All right, so this is the 10 assumptions which we should follow, which the OLS should be fulfilled to ensure that the model that we estimated are a good model in that sense, the best model in that particular sense. So this is the 10 assumption. We go through one by one the assumption. This is like the 10 commandment in econometrics, right? That everyone should follow through and to follow closely, right? Or this in a much more latest environment. This will be called the strict SOP that you need to follow, the model need to fulfill to ensure that the model follow all these SOPs before it can decide that the model is the best model, the best chosen model. All right, so this we'll go through the assumption one by one. So assumption number one, assume that the model is linear in parameters, linear in variable. This has been explained in the previous chapter. What's the meaning of parameters and variables? It should be both linear in function. Right? The second assumption here means that explanatory variable or the independent variable should be non-stochastic. We know the word stochastic. Stochastic means random. So non-stochastics mean they are not random. In that sense, we have the variable. The explanatory variable are assumed to be non-stochastic in the sense that their value must be fixed in the repeated sampling. When we say fixed, it's not about the same value. It's about the x and the y having their own values in that sense. All right, so it's non-stochastic. So you can know the value because when we want to do the estimation, we know the value of x, we know the value of y, and this is also will be closely related to the other assumption which you're going to explain throughout this particular chapter itself. Right, assumption number 3, which is actually one of the most important. All the 10 assumptions are important. You can't really rank them. They are equally important in that sense. But here, we assume that the assumption assume that zero mean of disturbance. So to speak, zero mean of disturbance. So to speak that the expected value or the mean value of the disturbance is actually 0. The mean is 0. On average is 0. But individually, they might not be 0. They can be positive. They can be negative. But on average, when they added up, they are 0 in that sense. Yeah, when they are 0, if you see this equation, when they are 0, for example, like this, right? This alpha plus beta x, right? Beta x plus a mu here. When this is 0, means that we can easily solve this equation. So that's the idea here. Again, but the funny thing is that why do we include that at the first place? The error term, we already exposed you with that in the previous chapter, saying that why need to include error term. The reason behind of error term inclusion is important for the regression itself, right? To highlight several important materials of stochasticness into the model. All right, so for example, like this, right? You can have the kind of error term here, but you add it up, is actually, or on average, is actually 0 in that sense. If you still remember back, the previous chapter talks about the plot, the graph, and the plot like this, where we have a plot like this, right? And uneven, but we try to plot a straight line and talks about linear regression. So all these plots, actually we linearize them in that sense first, and also that if this dotted is the error term, means that on average they are assumed to be 0 in that sense. All right, based on this assumption. So assumption number 4, which is very much related to the next few chapters, talking about heteroskedasticity. Right, repeat that, heteroskedasticity here, skedasticity or skedasticity in that sense, which is actually assume that homoskedastic means that equal spread or equal variance. Hetero means that not equal variance. So what does variance means? This is based on the assumption, based on the proposition, and use the assumption. Right? Move to this next slide. So this means of homoskedastic in that sense that we assume that the expenditure are the same. We assume that throughout the sample that the behavior of the consumer assumed to be constant, not changing. Right? You always put that as a part of our assumption, especially in economic analysis assumption. Right? But this can happen. Heteroskedasticity will disturb the regression if that happens because the expenditure, let's say, are not the same. Let's say you can imagine that there are differences between high income, middle income, and low income. Certainly the expenditure pattern also different. Here we assume that everyone else spend equally the same. Here the assumption that it's not the same. Right, so this is heteroskedasticity. We'll go through that more detail in the chapters when we come across. So, but this is the assumption number 4 in that sense. Assumption number 5 is autocorrelation, or we call it serial correlation from the word serial, means that repeated, the correlation are repeated, auto, repeated. It's like automated, so repeated in that sense. So the correlation between the idea is that there's a there are correlation between the error term of one period of time to the other period of time. Here, just now I forget to tell you, the heteroskedasticity only happens in cross-sectional data. Autocorrelation only happens in time series because the elements of time here is important, right? Modeling time series data means that I mean, whatever happens this year going to impact next year, like the coronavirus, that like the COVID-19, that what we're having here since last year, since 2019, have we brought forward to 2020, brought forward to 2021, and might be 22, 23. The impact is still there. Means that the correlation can assume that this impact is like a correlation. So the error term of 2019 is correlated with error term of 2020, and 2020 error term is correlated with 2021 error term. So we do not want that to happen inside the regression. No autocorrelation. Again, we will go through this chapter later in the semester. Right? This is the example. No systematic pattern. This is what we want. This have positive and this is have negative correlation. This is what we do not want. This is what no, and this is the no here. All right. So assumption number 6 that says that we assume that the explanatory variable and error term have separate influence on the dependent variable. Right? Means that they are not correlated. Why we assume that in that sense is that we want the whole idea is that we want to know the impact of X towards Y. That's the main thing. And also we do not want the error term to disturb it. Although it's called error term, right? So it means that we want to differentiate or distinguish the impact of X towards Y, and to distinguish the impact of error term towards Y, also the epsilon towards Y, right? Towards Y, right? In this sense. So this is assumption number 6 in that sense. Number 7 is a very common thing that and then is applied towards the sample size. Means that the observation, the sample size certainly must be larger than the parameter to be estimated. All right. So in that sense is that the sample size must be large enough and large enough comparatively to the parameters of the variable to be estimated. Large enough. And this large enough also very much related to what I'm saying in the beginning just now, talking about the sample to represent the population. Number 8 here is very much closely related to number 2. We still remember just now number 2. Explanatory variable are non-stochastic. So we have number 8 that represent variability. This is variability. All right. So this is variability, means that there are values and there are different values of the X. Even though you have a fixed value of the X, like for example, interest rate, exchange rate might, if you are in the fixed exchange rate regime, then the value is the same in that sense, or the interest rate which do not change for some years or some quarters. But then again, it still have some variability in that sense, the X especially. Number 9, here we can use it, we can test this condition with Ramsey reset test. All right, number 9 here is related to reset, a test by the name of Ramsey reset test. All right, let me write up this word reset here. Ramsey reset correctly specified means that there might be no specification error, the use of the choice of the correct model, and then use the choice of correct functional form, the variable use are optimal in that sense, and so on. So this assumption could be tested in the later chapters of this class. Number 10 is perfect collinearity in that sense. We do not want perfect collinearity. Means that this is the issue of multi-collinearity. Multi, I just write the word multi, right? Multi collinearity. So multi-collinearity means that they are collinearity between two explanatory variables. The whole idea here is very important, very interesting. X supposed to explain Y, right? If you have more than one X, maybe you have one X1, you have X2, right? You have X3, you have X3, you have X4 in that sense, right? These four variables supposedly explaining Y, but this problem exists, perfect collinearity or multi-collinearity exists when rather than X explaining Y or the X's here explaining Y, the X explain the X itself. So that's the interesting issue, right? It's like you're having a proper scandal with the Y, but then again you have your own scandals inside here. There's a relationship between here and here, this one and this one, so it's a complicated. Remember our first chapter talks about simplicity. Simplified our relationship. Do not have scandals all around to complicate the kind of relationship. Oh, sorry, it's relationship. Anyhow, so that is assumption number 10. So we have 10 of the assumption. One more assumption that's often used in the practice but not required for least square is talking about normally distributed. So we follow normal distribution where the error term is normally distributed with mean zero and variance sigma square. Variance sigma square in that sense. So the error term is normally distributed. This is how the write up is, right? This is how the write up mean zero and sigma square variance, right? Error term is normally distributed with mean zero and sigma square variance, right? So if you have the book, the book Gujarati itself, in the page, you can have a look of how this important assumption bring forward in that sense. The normality assumption are important also. We're going to test this normality, whether the error term is normal. We can use it using a simple test called Jacques-Bera. In short, it's called JB. This is nothing to do with Justin Bieber. The JB test to test the normality assumption, right? Especially when dealing with hypothesis testing. So we have finished up the first part, which is called the assumption of classical linear regression. Now we move forward to the second part, which is the blue properties, right? BLUE, yeah, related to color blue, right? Best linear unbiased estimator is what we call as blue. And the blue properties have these four properties that should be fulfilled so that we can conclude that the estimator, when I say estimator, means that the estimation, the estimator that you do, the inferences that you do, statistical inferences, best linear unbiased estimator, which lies the four component inside, four elements inside there. They must be linear, bias, efficiency, and consistency. What is this? We'll go through here one by one. So it must be linear. This is support back the assumption. Must be linear in variable, dependent variable and parameters, right? Estimator is unbiased. The next one, unbiased, if the mean of the sampling distribution equal the true parameter. The nearer the better. The nearer the better means that the sample does matter here. The sample must be big enough to represent the population. So that is unbiasedness. If you adopt in that sense the other words of unbiases, perkataan berlawan dia is actually called bias. So rather than we are biased, then this estimator are unbiased, right? So in that sense, if this is called bias, then this is called unbiased, means that the mean of the sampling distribution equal to the true parameter in that sense. All right, so this is just the example here. This is the example of that. Right? Unbiasedness can be represented in such a way. This is unbiasedness is always the one that if it's plot in normal distribution is always the one that lies in the middle. This is called bias. The other side is bias underestimate, bias overestimates in that sense, which we do not want for our regression. All right, for the estimator. The next term, the third one here is called efficiency. So we want the best unbiased or efficient estimator refers to the one we have a smallest variant among the unbiased estimator. Among the unbiased some more. It must be unbiased first, then you have the smallest variance. Smallest variance very much related to the homoskedastic and related assumption from the earlier one. All right, it is unbiased estimator with the most compact or least spread out distribution because variance is like a spread of this this dispersion in that sense in terms of the graphical representation. Right. Another word of saying this is that an efficient estimator has the smallest confidence interval and more likely to be statistical significant than other estimator. Right. You find the best in that sense, the most efficient. Consistency also very much closely related to the sample in that sense. An estimator is said to be consistent estimator if it's approached the true value parameter as the sample size get larger and larger. Asymptotic unbiasedness. In that sense, as the sample size getting larger and larger, we are close to the true parameter. What is the true parameter? Is the population parameter, the population. We want to achieve as close as possible to the population with the sample that we use. All right, so that goes back to this idea of having this consistency. So that's the four important elements in blue. It must be linear, it must be unbiased, it must be efficient, and it must be consistent in that particular sense. And surely it cannot run away with normality distribution with mean zero and sigma square variance. Right, in that sense. We move forward to another part which is important also for what we expand on goodness of fit. Right, what we call goodness of fit in that sense, which is very much related to the terms goodness of fit, is called R squared. Right, R squared, the measurement of goodness of fit to know whether the model is good enough and fit. Like how we can say that we are fit, we're healthy and fit. All right, so there's a measurement of fitness. So here's the measurement of fitness for the model, which is using R square in that sense. Right, so R square value, because it's a square value, so it will be positive from 0 to 1. There will be no negative value of R square. If you get a value of negative of R square, there might be something really wrong because it's a square. So this is the formula to calculate it. So how to interpret? If R square is 0.89 means that 89% of variation of Y been explained by the X. The higher the R square, the better the estimated regression model fits the sample. Means that this is goodness of fit. The higher, the better fit. The lower, not so fit. Not so fit in that sense, right? It translated into that. That's the indicator. The better, the higher, then you're much more fit in that sense. The model is much more fit. All right. So, but the idea is that it's not suitable to compare two regression model with the same dependent variable but different numbers of independent variable because R squared do not taking care of degree of freedom. So if you want to compare two, then this one or in other words, sometimes it's called the goodness of fit is also called coefficient of determination, right? To determine, right? So this is R square 0. This is R square. How R square looks like, right? R square equal to 1, right? And to solve the problem of comparing between two models, we can use a measurement called adjusted R square. The adjusted R square, which are adjusted for the degree of freedom here. Sample and the parameters are used in that sense, right? R square is always positive, but adjusted R square can be negative. and you can compare between two in terms of to know that which model is a better fit, have a better fit in that sense. Here's an example, which we're going to do this in eViews. This is an example of output from eViews. Right, this is the real example. Alright, this is an example of the R square. So the one I put in red here is the R square and the R square, adjusted R square. What's the value? N is 6 here. Observation is 6. The R square here is 0.996 and the adjusted R square is 0.995, a bit lesser than the R square. Interpret the variable as are they significant? This will be a good question for the class, for our online class. I'll not tell you about on that in here in the video, but we're going to interpret that inside the online class when we do this chapter. All right, so bear in mind on that, have a look on that, whether this is significant, especially the x. This is the constant, the c. Are they significant? Is variable x significant? Right? So R square is only the descriptive measurement. R square, adjusted R square does not measure the quality of the regression model. So certainly you need more indicators to ensure that you have, if you want to compare, to ensure that, to know the quality, to ensure that what type of indicator and make conclusion whether this is a good model. R square is just one of the indicator. All right. So this will be the end here, but we are not ending yet because I want to mention to you about this part just now, the normality assumption. The normality assumption. Additional a bit. This is like you finish up the movie. This is extra 5 more minutes to go. All right. So what is normality assumption? All right. Normality assumption takes into consideration whether they are normally distributed. Certainly, as I mentioned just now, normally distributed. We want to know whether they are normally distributed. Under the normality assumption for error term, this is error term. OLS estimator beta and beta 2, beta 1, beta 2 are normally distributed. Right. In that sense, normally distribution. So this is the properties of normally distributed. Surely it's related to the blue and related to the assumption. There are unbiased minimum variance. Remember that, efficiency and consistency. So this is the blue properties in that sense. The blue properties also support the assumption of normality. Right, normal distribution in that sense. This is all the related slides. Right, on the normality assumption. We can, as I told you, we can test that using the JB test or Jacques-Bera test. We will do it when we deal with the eViews in time to come, weeks to come here. All right. So, and you can have a look of this chapter also. It's an interesting one. This one I got it from this one is from the book, the soft copy book that I give you, that I put up in the Ellipse system. This is one of the book. It's called Econometrics for Dummies, chapter number 4. Have a look of that. It's an interesting chapter to go through. Right, interesting chapter to go through. Oh no, it's not from Econometrics for Dummy. This is from Introductory Econometrics for Finance. This part that is more on that part, but this is what we are covering up. Right. Yeah, the classical linear regression model assumption and diagnostic test. This is further on the diagnostic test, which we yet to go through. Right, we yet to go through, but surely that we can do that and in eViews. But here is the assumption. The first part will be the assumption. The introduction will be the assumption. All right, and then yeah, this is the assumption here. You can read through the assumption. The first part of it, on the assumption, talks about zero mean and all these assumptions, and how we can solve the problem of heteroskedasticity, autocorrelation, and so on. Right, this will be the eView output, which we will go through this semester. All right, so I will stop here for now for this particular chapter. Surely that take care everyone, stay safe everyone, I'll see you in the next chapter. So adios and bye bye.